Okay. All right, so we got our book out. All right, and we're looking on page 113. We're looking at number 19. Now, all you're going to do here on these problems is list the functions that in number 19 are odd. Now, have we talked about what odd means?
Yeah.
What did we say? It has to do with the symmetry. If you are odd, you're symmetric about the origin. So you'll remember OO. We're symmetric about the origin. Now, what that means, let me give you an example of one. One of the four, and you can tell by looking at the picture, one of the four that's odd is the identity. Here's the origin. If you were a baseball player and you threw a point, this point, across the origin, it would land down here, right? It would land on another point on the line. That's what it means. So that's an example of one. Can you think of another one that's odd, that you could throw points from quadrant 1 into quadrant 3?
Cubing.
Cubing, perfect, Paul. That is exactly right. That is another odd one. If you took these points and threw them over here, they would land right on other points on the picture. The book says there's 4. Can you think of another one?
Would reciprocal be one?
The reciprocal function. Paul, I think you've got this figured out. That would be one. That is exactly right. If you took these points and threw them over here, they would land right on that curve. The last one is a little bit harder.
Sine.
That's it. The sine function. That's the one. The sine function is odd. It's a little bit harder to see, but can you see if you took this bump and threw it, it would be this bump?
Mm-hmm.
These are your 4 odd functions. Okay? Those are your 4 odd functions. Now, I don't want you to memorize that. Oh my gosh, your brain's exploding. You have too much to memorize already. What I want you to memorize is, what does it mean to be odd? It means points in quadrant 1 end up in quadrant 3, and points in quadrant 2 end up in quadrant 4. That's what odd means. So when you look at a picture, you can tell if it's odd, if that's what happens. Okay? All right, next question. I'm going to look at 20. The 6 functions that are increasing on their entire domain. Do not be confused. Increasing means exactly what you think it means. Getting bigger. So I've got one right here. When I draw this picture, left to right, which is the way I read, when I draw this picture, which way is my pen going? Up. That's increasing, John. 113. So one of the 6 is right here. The identity, that's increasing. Let's just use the ones we got on the board. Would you say this one's increasing? Left to right, which way is my pencil going? Up. Always up. That's increasing. Let's look at this one. Left to right. Oh, wait a minute. Which way is my pencil going?
Down.
Oh, so that's not increasing, right? That one is not increasing. How about the sine curve? Now, is it always increasing? That's what the question is. No, this one's going up and down. Okay, so we've got 2. There's supposed to be 6. So can you think of 4 more, look at your note cards, that when you draw them, the only way you go is up?
Greatest integer.
Greatest integer. Exponential. Yeah, somebody said quadratic. Let's look at that one. Is that one always increasing? No, it's decreasing on this part. It's sometimes increasing. Square root, always increasing.
Logistic.
We got the identity right here. Logistic, yep, logistic, always increasing. Exponential, we already got exponential. Logarithmic. Now, somebody, this one is tricky. This one, I hate this function. Somebody said greatest integer. All right, so wait a second. The 6 are here and here. These are always going up. And then here, 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 and here. There are the 6. Now, somebody said, what about the greatest integer function? This is so confusing because if you just look at the steps, what are the steps doing? They're going up. So you think that's increasing. But I want you to look at this step. What's happening on this step alone? Just this piece of it. Yeah. Is that going up? No. Is this one going up? No. Now, if you look at the whole big picture, the steps, individual steps, you're going up as you go from step to step, but each step is not increasing, so it isn't increasing everywhere. Does that make sense?
Mm-hmm.
That one's a confusing one. Okay, good. All right, next we've got 21. What does it say? The 3 functions that are increasing on the interval, no, decreasing on the interval from negative infinity to 0. Okay, so think about what that means. That means that as you go, as you draw it, here's negative infinity and here's 0. So over here, whatever you draw over here is going down. That's what the problem says. That in this space, over here, when you draw it, your pencil's going down. I have one on the board actually. What about this guy? Is your pencil going down?
Mm-hmm.
Can you think of another one? Don't say this one because it's going up and down, so that's not one. So you think of one, look at your note card. Over here, on this side, when you draw it, you go down.
Absolute value.
Absolute value, absolutely. On this part, it's going down. Squaring, absolutely. On this part, it's going down. How many were there supposed to be? 3, we got them right there. All right. These questions are pretty easy. If you look at your pictures. Okay. The 3 functions with infinitely many local extrema. Now, what we mean by local extrema is high points and low points. So I'll just give you a hint. One of them's right here. Because as you draw the sine curve forever and ever, what have you got? You've got tops of hills all over the place, and then you got bottoms of valleys all over the place. So when we say infinitely many local extrema, we mean lots of high points and lots of low points. This one has a low point, but it only has 1. And this question says infinitely many. So one of them would be the sine curve. Well, then obviously another one would be the cosine curve, because they're the same, basically. Can you think of another one, Robbie? It would be, and that is so hard to grasp. Good job. I mean, good job. That is so kind of confusing. But within each interval, if you look at just this interval, that's the high point. Here, that's the high point. Here, that's the high point, and so on and so on and so on. I hate that function. But yes, that's it. That's it. 23. The 3 functions with no zeros. All right, now wait a minute. What do we mean by zeros? What are we talking about when we say zeros? X-intercepts. So there must be 3 pictures that don't cross the x-axis. Do I have any of them up here right now? This one doesn't cross the x-axis, does it? Which one is that? What is this? This is your exponential. What about this one? This one doesn't cross the x-axis. This is your logistic function. So there's 2 of them. There's supposed to be one more that doesn't cross. Oh, this one doesn't cross the x-axis. Now I heard somebody say logarithmic. Does your logarithm cross the x-axis?
Mm-hmm.
Yeah. So that one we got the 3. Good job. 24. The 3 functions with range all real numbers. Now don't be confused. Range is y. So if the range is all real numbers, that means the picture goes all the way down and all the way up with no breaks. Okay? All the way down and all the way up with no breaks. Is that an example of one?
Mm-hmm.
All right, so one of them is the cubing function. How many am I supposed to have? 3. All right, one of them is the cubing function.
Logarithmic.
One of them is the logarithmic function. All the way down, all the way up, perfect.
Identity.
And the identity. Now, I know what some of you might be thinking. Some of you might be thinking about this guy. Because, does it go all the way down? Yep. Does it go all the way up? Yep. But what does it have right here? A break. If your range is going to be all real numbers, you're going all the way up and all the way down, and you're not broken in there. You're not skipping anything. So the answer is the identity, the logarithm, and the cube. All right, just a couple more. The 4 functions that do not have end behavior, oh man. We haven't talked about this, have we? This is going to make us feel like real mathematicians. All right, it says the limit as x approaches infinity of f of x equals infinity. Now it says there are 4 functions that do not have that end behavior. All right, so let me tell you what this means. And I'm going to use my friend the cubing function as an example. This says, as you let x go to infinity. Okay, so that's this way, right? So we're going this way. We're marching out this way, plotting points. So out here, we're plotting these points, okay? As x goes to infinity, y, f of x is y also goes to infinity. So that means as you go out, you're also going up. This says x is going to the right. This says y is going up. So in this picture, as I go to the right, do I also go up? So any picture that shoots up like that is going to have that end behavior. Now, this says, give me 4 that don't do that. Clearly this one does. Does the parabola do that? Yes. Does the V do that? Yes. Find 4 that do not do that. Sine and cosine. What do sine and cosine do? Up and down, up and down. They don't shoot off into space. They're doing up and down, up and down. So 2 of them are sine and cosine. Can you think of another one that does not shoot up into space? You gotta be careful with that one. It actually does kind of just keep marching on the way. Reciprocal function. Did I erase that? Look what happens with the reciprocal function. As you go right off the page, here's where x is going to infinity. What's happening to your curve? Is it shooting up? No, it's levels off, doesn't it? So that's another one. That's another one. I've lost track. What have we named 3 so far? It's supposed to be 1 more. The logistic function. What does the logistic function do? The farther out I go, the higher it gets, but it doesn't shoot up into space. It levels off as it gets closer to 1. It has a ceiling. It has a cap. So those are the 4. Very good. You guys are pretty good at this. Let's do one more. Number 26. Okay, now tell me what 26 means. As we go to the left, it goes down. See, look, it says the limit as x approaches negative infinity. Okay, so that now we're going this way. The function, or y, also approaches negative infinity. So which pictures, as you go left, you also go down? As you go left, you also go down. What about this one? Does that one go left and down? How about the identity? As you go left, do you go down? Can you think of any other ones? As we go left, we go down. How many are we supposed to have? 3? We have cubing and we have identity. Reciprocal, let's look at that one.
Logarithmic, maybe?
As I go left, I'm not really going down, I'm kind of leveling off there, so that one doesn't count.
Logarithmic?
Logarithmic is a little bit tricky. We'll talk about that in a minute. Let's see if we can find another one. Well, it has to be on this side, it's going down.
Oh, okay, okay.
On this side, it's going down. You got the identity. You got that. That's the identity. You got that one. So far, we've gotten the identity and the cubing function.
Cosine?
Ah, greatest integer. What happens to these steps? I don't have them drawn here, but what happens to these steps? The farther to the left you go, what are they doing?
Going down.
Going down.
So.
Now, Christian, do you understand why the logarithmic curve doesn't work? It's not even over here.
Yeah.
Yeah. Okay. You guys did a great job. Super. All right, so now you can put your book away. Keep out your note cards, though, if you would, please. Because you'll notice in the next thing we're doing, you are going to be doing a little bit of sketching. Okay? So I want you using your note cards. To help you. All right, problem A. Says graph this. And you're thinking, oh my gosh, Mrs. Ford, it's kind of hard. Actually, it is super simple if you know a couple of things. First of all, you need to know what the square root function looks like. And you should already know that. What does the square root function look like? This, right? Any square root picture is going to be some variation of that. What we're talking about now is how we do the variations. So one way to do variation is to stick a number in the problem. Now, here's the tricky part. It is different if it's the square root of x minus 5 or if it's the square root of x minus 5. Those are different problems. And the graphical impact is different. Anytime you add or subtract to the x, so you like group it with the x, you're taking the square root of the whole shebang, you're grouping it with the x, that's going to move you sideways. And as is always the case when things are grouped with x, if it's x minus 5, it's going the opposite. So this would be positive 5. So if it's a minus 5, it goes this way. If it's a plus 5 or whatever the number is, it goes this way. So when I'm asked to sketch this, oh, I see it's grouped to the x, that means it's going to shift this way. It's a minus 5, that means I'm going to take 5 steps to the right, opposite of what I think I would go. I'm going to go 5 steps to the right, and I'm going to draw my picture. That's it. That's all there is to it.
Would there ever be a time where the angle of the line goes like the other way?
Oh, yes. We'll talk about that in a minute. Hang on to that thought. Let me finish this one first. I can finish this one first.
Okay.
If I group with the x, it's sideways, because x is sideways movement. This one is not grouped with the x. So what do you think that's going to do? That's going to take you down 5. If it's not grouped with the X, if it's just a number stuck on the end, it's gonna go up or down. Positive goes up, negative goes down. And I'm saying 5, it could be any number. So if we had to graph this one, we would take this shape and drop it down 5 units. So it would look like that. Same shape, just repositioned. Adding and subtracting numbers just repositions. You pick it up, put it down somewhere else. Let's look at B. Now, this is a different shape. This is an absolute value problem in B. So what do you think that shape's going to be? What's the absolute value shape? It's a V. It's going to look like this. Robbie, you're going to get out of here soon enough, sweetie. You need to pay attention. It's good. It's all good. Now, we have a V. This, so if that weren't there, you'd have a V. Now, but it's got a +1 tacked on the end. What does a +1 tacked on the end do? Move it up 1. So on your paper, you are going to sketch this. It's that easy. Okay, let's look at C. Now, 2 things kind of go through your head when you look at this. The first thing is, okay, what's the shape? This is why you had to memorize those flashcards. What's the shape? It's the exponential. So the basic shape is this one. And remember, Mrs. Ford made you mark this point. That's your exponential. That's this, right? Now, the second thing, so first you got to remember the shape. Second, you got to remember what this 1 does. You know it picks it up. Anytime you add or subtract, it picks it up and moves it. You got to pay attention to where that 1 is. Is it grouped with the X? No. If it were grouped with the X, it would look like this. See? If you can put it in the parentheses with the X like that. I don't know what that was. That's what I'm worried about. I hope it's not some kind of animal.
Oh, no.
I know. Okay. So if it's grouped with the X, that's going to move you sideways. This is not. So this is another one where I'm going to simply do what? Move it up 1. Now, I'm going to move it up right here so that you can see. I'm going to move it up 1. So that point now would be 0, 2. And where this asymptote was, see how it's getting closer to 0? Now it's going to be getting closer to 1. I said I was going to do it green, and then I did it black. But that's the point right there, or that's the curve right there that we're talking about. The asymptote that was down here on the line got moved up 1, just like everything else on the curve. What about D? It's the squaring function. So the first thing that pops into my brain is parabola. Now you don't have to write that down. It's what pops into my head. Okay, I got a parabola. Now, what's going to happen to that parabola? It's going to move. Look where that +1 is. Is it grouped with the X this time?
Yeah.
Yes, which means it's going sideways. And remember, the X motion is always opposite. So we're going to go 1 unit to the left. It's +1, we're going to go 1 unit to the left. There's the picture. What about E? situation. It's a parabola. The difference is it moves down. Down one. If I wanted to move it to the right, I would have to have this equation. If I want to move it to the right, I'd have to group it with the x. This is a picture of what's on the paper. All right, now I want to get to this question about, will they ever like be upside down or flip this way or whatever? I'm gonna run out of time, so we'll pick this up tomorrow. But quick recap. No, I'm gonna start it. Quick recap. If you add or subtract, what happens? Add or subtract a number, what happens? It moves it. Up, down, left, right. It moves it. If you want to turn things upside down or flip them around, you have to put a negative into the problem. So, there are two ways to put a negative in. You can put a negative in like this, and you can put a negative in like this. It's the same distinction as before. If you're changing the sign on the x, if you're grouping the negative with the x, and then doing the function, that is a reflection across the y-axis. This will flip across the y-axis. If you stick the negative out in front, it flips you across the x-axis. Upside down. So, if I had this equation where the negative is grouped with the x, that would take this picture, my normal square root picture, and make it go this way. If I put the negative on the x, it takes it across the y-axis. If I did negative root x, it would flip it upside down and it would look like that. Okay? So, adding and subtracting picks you up and moves you. Negatives flip you around, either up and down or sideways. Okay?
There you go, blow it out.
All right.
So good.
All right, go. I will see you, I hope, tomorrow. Have a great day. Have a good lunch or whatever you're doing now.
Since I won't hear tomorrow, just check the video.
Yes. Yeah, because we'll take a bunch of notes tomorrow.